Thank you for having me. And after 3.5 years, I think we calculated, at last physically we meet each other. So we've been in support of this technology project through Alcore. We were invited by Mark through a reference in the Fluorine network internationally, and that's how we got to speak to Mark. And in this presentation, I'm going to give you a bit of a background of who we are, and out of that, you will develop a much better understanding also of where you are and what your opportunities are, which are actually quite big. So the benchmark or the analog that was put and by Mark and Alcore was to look at the way aluminium and trifluoride, but before that, and the anhydrous HF is produced in the classic sense from fluorspar. Fluorspar being the mineral mined, of which South Africa actually has some of the largest reserves on the planet, together with China and Mexico. So we have got major experience in the production of HF through the fluorspar route. And that's where the interest and then the first meetup happened between us and Alcore. So if I just need to figure out here the buttons. Okay, so the purpose of this first presentation, which will be followed then this afternoon by a second one, is to introduce us and illustrate experience and expertise that we bring to the Alcore project, to provide an overview of our global supportive network, because we function globally, and that is facilitating the development then through us of the proprietary technology on your side. I think on that point, what is pertinent to you is that the agreement between us and Alcore is that all IP that originate during this period where we are supporting you accrues to Alcore. So we're not going to claim any IP royalties and things like that going forward. For us, it's a much cleaner process. You are footing the bill, so we feel it's a fair agreement to have. So all IP coming out in this proprietary technology belongs to you. We will not have any future claim on that. And then, like I've already said, to assist you to develop a deeper understanding of your technology and where it fits into the environment, not as in the green environment, but as the business environment, the technology environment, and then the fluorochemical value chain, which is then opening up to you. The content then is our background of where we are, who we are, our current project, which is actually on the fluorine side. Now, fluorine being the F part of the HF, is a gas, which about 10% of the value chain applications comes from fluorine as the building block versus hydrofluoric acid as the building block in the value chain. Then a short description of a very high-level description of the fluorspar process, which you will see if you will be able to recall the diagram that Mark has put a bit earlier. You will see that they are very similar and there's a fit. And then I will give a very brief description of, from there, what the differences are. Then the supportive networks, the balance of business, will then go forward into the second presentation of, and the other opportunities that exist for you. And then a bit of a focus on towards you, mainly on the way forward, and what you can expect going forward. I do not have a full slide of a disclaimer. Usually the disclaimer is a full slide. For us, it's quite simple. Everything I say, don't make decisions from it. Ask questions, but it's for discussion purposes. So don't quote me that I told you something of which you've lost money. But alternatively, if you make a lot of money of what I said, good for you. I will not come claim. Okay, let's drill down a little bit deeper. The equivalent of what you are doing in the aluminium industry, fluorine, is actually way more critical than just being called a critical element. It's most probably one of the widest used elements on the periodic table. Quite a few industries will not be in existence if it wasn't for fluorine, of which actually the nuclear industry is one of them. To enrich uranium into nuclear fuel, you need to get your uranium into a gas form. And that is done by reacting the uranium with HF, hydrofluoric acid, to produce UF4, and from there on to react it with fluorine gas to get to UF6. The reason for that is you want uranium, which is a metal, into a gas form, so that you can, through a centrifugal process, separate the isotopes. The radioactive part, you need to increase the concentration to get to the nuclear fuel. So without fluorine, the nuclear industry, as we know it, will not exist to enrich the uranium. Isotope separation into other metals is also happening with fluorine, molybdenum as an example, and quite a few others. The same key role is played by fluorine in the aluminium industry. So aluminium on the one side, but without fluorine, you will also have difficulty in producing fluorine primary metal, but then the part Mark has touched on it, but it's something that you need to pay much more attention to, because that's one of your big opportunities, is the aluminium alloys. Just as you use aluminium trifluoride in the primary smelter, in the induction ovens going downstream into the alloys, the other base metals also come in as metal fluorides. The titanium that goes into the one category, or I think more than one category of the aluminium, is introduced as a titanium fluoride. The boron that goes in as a fluoride, and then from there also the silicon can go in as a fluoride. So there's a key role downstream as well for fluorine, and it's an opportunity for use, because once you have the HF, you can do the master alloys as well, going downstream into the standard alloys as well. So your exposure to the aluminium industry is actually wider than just the primary aluminium trifluoride. Okay, so coming back to us, we come from the 80s, we come from the nuclear industry, where we were a bunch of entrepreneurial engineers, all of us mainly chemical engineers, called the applied fluorine engineers. And that was in the 80s. We were, in the nuclear industry, we were commercializing technologies out of the laboratories. Through efforts in South Africa, the parastatals were attempting to commercialize. So with the bunch of scientists developing technologies to produce, for instance, the base metals, fluorides, tungsten fluoride was one big project we had. The titanium fluorides was my first project out of university. I designed the pilot plant, and from there we commercialized that plant together with KBF4. So that is a full loop. And then through this, in the beginning of the 2000s, there was a South African expansion initiative, fluorochemical expansion initiative, where we then came back into the loop, and as part of our economic development strategies to process our minerals full value chain. That was the intent. So seeing that, that is where I then put Bifleur together, and in the network of the applied fluorine engineers, we started doing consulting work, first of all, on the safety side, doing risk assessment, major hazardous installation, authorizations, environmental impact assessments. So from that, we started offering these specialized technology commercialization services into the industry. And with particular focus then on the collect, that's where our buzz phrase, bring it all together. From the business perspective, from the market perspective, we put these technologies through the loops, and our experience of that first part from conceptualization through to the bankable feasibility is actually a very black hole environment. You throw all these resources and money into the black hole, and every now and again you get a big stream, hopefully coming back. So, it's actually a phrase that popped out in the last few months, is that building escape velocity from the black hole is something that we do. So, and in some moments we've been successful doing exactly that. And that is actually what you're busy with. You've got a black hole here into which your resource goes, time, effort, ideas, money, and you're busy building the escape velocity out of that black hole to get into a unique, and your process is a proprietary, quite a unique one, like Marcus already explained to the question. Okay, so our experience is then the full fluorochemical value chain. We have worked on most of the sub-segments. The fluorochemical value chain is divided, Marcus already mentioned, about a third into the aluminium industry, aluminium trifluoride. So one of the opportunities which you need to understand, which will come later, a bit later in the presentation and this afternoon, is the fact that because the aluminium trifluoride process is a short one, from fluorspar to HF to aluminium trifluoride, it's a three-step process basically into the end use then. Whereas things like the refrigerants, which is another leg, the fluoropolymers, which is another leg, pesticides, herbicides, all of them has got a few more segments in the value chain to cover before it reaches the end use point. So every Tom, Dick and Harry that wants to put up a HF plant runs for the gate of producing aluminium trifluoride, which created quite a bottleneck internationally. So new HF plants is problematic because you need to build a huge one. 60,000 tons has become the minimum standard. Honeywell in the States run 130,000 capacity plants. The Chinese also to that scale. So these guys needs to build, but to justify the investment into those large scale, you need offtake. I mean, the key element of any investor is offtake. Do you have a customer? Do you have somebody that will buy the product? Which is the key primary reason to be in business, is to have a customer. So to sell and find offtake for that size of HF plant is rather difficult. With most of the aluminium trifluoride capacity taken, but there are other gates that has been opening now. The whole battery environment has opened quite a few new streams and offtakes. The environmental pressures on some of the fluorochemicals on the refrigerant side has opened other avenues. So with you then coming in with a smaller scale production at a highly competitive production cost opens up quite a bit of leverage for you to much more easily commercialize into an offtake, because the balance, the size of big HF production versus a multitude of of small end users required to make up the offtake for the big one, you are in a much better position. With a smaller production capacity that is already financially feasible for just one or two offtakes on the other side. So you've got a much easier road to the full-scale plant and to have a commercial unit. Okay, so what have we done? Like I said, when we started on, there's attempts in South Africa to build these huge HF kilns from fluorspar, which I've just described to you as being quite a difficult process, which was up to date not successful. And two of those projects, we were a part of the owner's team, so we understand the fluorspar process in detail. And that is then the expertise that we bring here from the chemical engineering perspective, and the equivalence between the process that you develop and the fluorspar process, of which we've worked on two of the 60,000 ton projects for HF specifically, but both of them were also into aluminum trifluoride. So the technology supplier for the aluminum trifluoride, we know quite in detail. We've got a very close relationship with them in the network. So we can assist you all the way to your full plant. We've also done technical due diligence for an investor group on the second one. So we also understand the investor requirements regarding these plants from that due diligence. And then, like I've coming full scale, we've got in-depth understanding of the application of fluorine then in the aluminium industry, not just for aluminum trifluoride, but then for the other base metals as well. Currently, on the fluorine side, in our efforts, we came across a customer that was looking for fluorine. He had difficulties sourcing fluorine, and we said, well, why don't we design and build and commission a fluorine on-demand production unit for you? There you see the example. We're busy commissioning that now in France. It's a containerized unit. What you see on the one side is the compressor. So the fluorine is produced electrochemically from HF. And the first slide, you will see our HF, that's our HF storage and feed unit. So the hydrofluoric acid comes to us in transport vessels, and then we transfer it from the left. We transfer it through into our two vessels, which then forms the feed vessel. Quite a bit of what you saw around them is for the safety. They are in a catch pot if they should be leaking. All the nozzle sits at the top. So to make sure that if there's a leak, it will be gaseous, which can be extracted through the extraction system. We've got chiller units in there to keep the HF in liquid form, actually. So HF handling is then this unit of ours that we've designed. We've designed to international specification. It's been authorized now by the European authorities. Those are CE-certified pressure vessels as well. So that's the level of engineering we bring to your project. On the handling of HF, which is also for you one of your, the dangerous part of your process. So we will, in the engineering design, you will get international standard HF handling equipment, and together with the necessary safety systems to pass all the tests around that. Okay, so that's what we're busy with, the customers in the surface fluorination industry. And that's just to give you back to the critical element of fluorine. Your car's petrol tank will not be of plastic if it wasn't for the fluorine. The surface fluorination of that plastic, the polymer, seals off the tank, and you can have a plastic petrol tank. The herbicides, pesticides people in the agricultural industry, all their containers that used to be metal containers are now polymer plastic containers because they are surface fluorinated. So our client has got a unique inline surface fluorination process where when he blows the packaging, 1 liter, 5 liter, 25s, he at the same time that he blows the bottle, in the blow molder, he also there's a little bit of fluorine in the stream, and he then surface fluorinates the bottle and seal the bottle on the inside. That's why we've got that compressor in the system, because he blows with 13 bar nitrogen. So we need to get the fluorine up to 13 bar to blend it into the nitrogen with which he blows the bottle. So that is what you see there in front of you. It's quite an intricate exercise to get that compressor working effectively. Okay, so that's just a little bit of what our current project on our FGen. We've trademarked our FGen, and upon successful commercialization of this, we designed this from fundamentals. There's no external component in there. Everything that you see there comes from our brains. So we've trademarked, and once this technology is proven, we will be able to offer it. We've got quite a bit of requests already from a few small-scale fluorine users that is interested in us providing them with this technology. It's a new generation fluorine production using the same principles than all other electrochemical production, but we've made quite a few changes on that. Okay, just an overview and you will see that the HF from fluorspar is very similar, if not almost exactly the same as what you will be using on processing the bath. On the red arrow, the fluorspar comes in of which is, and later on I've got a bit of a comparison table to your process. So that's where you will bring the bath in. The similarities, the reagent is the same, the sulfuric acid together with the oleum into a pre-reactor, which is, if you look in the back now, the kneader that Zhao will show you is the equivalent, into then the HF reactor, which is a rotating kiln, which is the same again as what you use. Out of that, the HF comes into a purification section. Now for your, we have initially designed the HF purification section for you in your pilot plant, but the decision was then that we will rather destroy the HF into a product. In other words, we will immediately scrap it into aqueous HF, which you can sell. I had the question earlier around coffee. You will, out of your pilot plant, you will be able to sell your product already and get a revenue stream running out of your pilot facility, which is a bit out of the norm. Usually a pilot plant in the chemical industry destroys the product, but in your case, you will be able to develop your spec together with your customer, and you'll be able to get the revenue stream running at an earlier stage. At the bottom, the anhydride referred to there is actually gypsum. In the fluorspar process, gypsum comes out as the byproduct, where you will get the aluminium and the sodium sulfates as byproducts. And then there's a neutralization happening because there's a little bit of acid carryover. It gets neutralized, and what on the bottom right says anhydride is actually gypsum that goes into the building industry in the HF production from fluorspar. So again, similar to what you have. And then there's a big effort on the safety side, you don't want HF to release into that environment. So you've got scrubbers, absorbers, wastewater treatment systems. So there's quite a complex. Now in your case, that complexity will be used to produce your product actually in the pilot plant. So your scrubbers sitting there will produce product for you to sell. And similarly, as you scale up, you will be able to do the same. Okay, I've covered most of this fit to your project then, the feed material. There's a bit more complexity in your process, and which differentiates it from the fluorspar process. Calcium is the only counter ion in the fluorspar process, whereas in your case you've got aluminium and sodium in the bath. There's different reaction conditions, the thermodynamics and the kinetics are different, but it appears to be more friendly in your case, lower temperature, but then it's offset by the more complex byproduct then, which is the next one, gypsum in the one's case, but in your case, aluminium and sodium sulfates, which comes out together. There needs to be a separation into separate product. The one point here is that there is a loop back into aluminium trifluoride from this byproduct. The aluminium sulfate you can recycle back to aluminium fluoride, and then you can recover your sulfuric acid, which closes that loop for you. So if you don't find a market for aluminium sulfate, you can always recycle your own aluminium sulfate back into your secondary product, aluminium fluoride, and you can bring back the sulfuric acid to the front end of your process. So the fluorspar process is a very useful analog and a benchmark to one key element or one big driver of the cost here is the materials of construction, which are equivalent whether you use fluorspar or whether you use bath. On the acid side, you will be using the same materials of construction. So we've got years and years of experience on which are the better materials of construction to use. So in that sense, the engineering package will contain all that information. And you don't have to go into all kinds of experimental work with suppliers to find the best material of construction. So I will expand then in much more detail, tabling actually your successful and very exciting results where you are now at this moment. Okay, then there's another angle which we bring for you is our global supportive networks that we've developed since the 80s. We've been in the fluorspar industry. We've been presenting at the international conferences since 2010. We know almost every active player in the global industry in the fluorochemical side. So if we do not have the answer, we know who to ask, or who can offer the solution then. So the latest integration of our FGen actually then into the French network, because you will have to integrate your process as well into the Australian environment. We've got years of experience how to integrate new technologies into environments, business-wise, market-wise, supplier, spare parts, you name it. We've just took us about 14 months to integrate our FGen in detail into the French fluorine network. And in the laboratories to do analysis, sample analysis. It's not every laboratory that can analyze a fluorine sample. And so it was quite necessary to do that. Spare parts that you use, the pressure gauges that you use, all of them being special materials of construction, you don't buy them off the supermarket shelf. So it can get quite intricate. Facilitating the acquisition then of the necessary environmental and safety permits as well is another thing. Like I said, we've just had our FJ now authorized in the European environment, C certification and the works. So we will be giving you a lot of support in that sense as well. Okay, the conclusion is that, back to my coin that I phrased, the Alcore project is building strong escape velocity from the black hole. So into your pilot phase, your bench scale and laboratory have provided now excellent engineering information which we can pull forward. So the platform that you've established will assist largely and quite a lot into the detailed design for your pilot phase, and then going forward into the full-scale phases that is coming. Control systems needs attention into the pilot facility. So next up, scale up control systems, becoming major focus points, and then that balance of plant business components, which can also expand into the other products apart from aluminum trifluoride, of which you have now the opportunity to really. And there is a link to the rare earth as well. The neodymium rare earths into the magnets goes through a fluorination process as well. So on the rare earth side, you already have a spark between the two legs of your business. Thank you.
My name is Xiao Liang, the principal engineer of Alcore. Thanks to Chris just giving us a great summary of the fluorine and the HF industry. In this presentation, I'm going to focus more on the technical aspects of Alcore process to recycle fluorine from the aluminum smelter waste, tapped bars. The development of this process is progressing from the laboratory research work to a pilot scale studies. So this talk will cover a summary of our recent lab outcomes, the progress of pilot batch reactor experiments, and our plan to design and implement a continuous pilot plant in the near future. In the last 2 years, our research, lab research activities have advanced from bench scale static experiments conducted in the Alcore wet laboratory to a combination of using this modified laboratory rotary kiln with a ring mill and a muffle furnace. These combination setups allow for a better control of the reaction conditions and the capture of HF gas produced. So our primary objective to enhance the fundamental understanding of Bar's reactions with sulfuric acid and to maximize the fluorine conversion from Bars using the available laboratory equipment. In typical experiments we did, it normally starts by mixing and reacting Bars or any model compound with sulfuric acid at elevated temperature in this rotary kiln. This is the first step and can extract most of the fluorine out of Bars. In the second step, we'll use the muffle furnace to complete the reaction. The ring mill here is used to control the particle size of the processed material. Different methods and conditions are used here, aiming for achieving a high fluorine conversion. Over this period, we have conducted more than 30 runs with the rotary kiln and over 120 experiments with the muffle furnace. We tested different feed materials here. For example, the cryolite as a model compound of Bars, different real Bars waste from different smelters, and also fluorspar. These studies help us elucidate the fundamentals of Bars reaction mechanisms and optimize the process conditions. As shown in this figure on the right, we can achieve the different levels of fluorine from different steps from Bart's reactions. For example, here with the laboratory rotary kiln alone, it can yield maximum of around 70% conversion with a single pass. We figure out this limitation is because of the fact that reactant material is sticky and turns to form chunks during the transformation from slurry to solid state as the consumption of sulfuric acid. This will significantly reduce the reaction surface area and limited mass transfer. So to overcome this issue, we use the ring mill to crush the chunks formed. And as a result, you can see in the subsequent muffle furnace test, the fluorine conversion gradually increased to 90% after several passes. Through the extensive systematic studies, we have unveiled the critical factors for achieving high fluorine conversion. And more importantly, we also gained a deep understanding of the reactant material transformation during the process, which is a key factor for the design of reactor configuration. Starting from the tapped bath, so firstly, it has to be crushed from the centimeter size received from smelters to the micron level that's required for reaction. When mixing with sulfuric acid, it forms a slurry, a thick slurry like a porridge. And when the sulfuric acid is consumed and the HF is produced, this slurry becomes increasingly viscous and hard to agitate or move. Just like as shown here in this photo, which representing a 50% conversion material. It looks similar to making dough from flour and water. So as you may be familiar with, this process will require like significant kneading and mixing to ensure that the mixture to form a uniform consistency. So same for our Bart's reactions. We want the Bart's powder and sulfuric acid to meet at micron level homogeneously to promote mass transfer. As the fluorine conversion increased to above 70%, the material transformed from a white sludge state to a dry solid form that can be broken down to a certain size with minimum effort. However, if we want to push the fluorine conversion close to 100%, this material particle size needs to be reduced significantly with more power. The final solid product with a fluorine conversion very high that will remain as a fine powder with white color. So again here, maintaining the particle size and the continuous mixing are crucial. So discover this reactant material transformation during the process is a key observation in our research work. Based on these findings, we proposed that a two-stage reactor configuration for our Alcore process continuous operation. The first stage will be a double shaft kneader. As you see in this graph on the left, the double shafts are arranged in parallel and will operate in co-rotation direction. The special design flights on the shaft are curved to provide sufficient mixing and agitation of a highly viscous slurry, and also providing the material conveying capability for continuous operation. The gaps between the shaft and the kneader barrel need to be maintained at a millimeter size to ensure the fine scale mixing. But for the entire kneader, it has to have a large volume for gas space and the HF gas evolution. As the material transforms from slurry to solid state, it will move out of the kneader and to the second stage reactor, which will be a rotary kiln with internal slug return system. The reason for us to use a rotary kiln at the late stage of the reaction rather than a kneader is because of the requirement to produce fine enough particle size for further reaction. Well, a kneader can typically produce produce a millimeter-sized particles, depending on the gaps between the shaft and the barrel. But further reducing these gaps to produce finer particles will compromise the mechanical stability and the lifespan of a needle due to its nature as a high-torque equipment. Rotary kiln is a typical configuration that's used in flow spar process because it can provide continuous mixing and milling. This internal slug return system is designed to bring the solid product at the end of the rotary kiln back to the front end at a desired ratio through this center channel. This design can provide several benefits. First, like this recycled solid, when it mixes with the slurry out of the needle, it can dilute the slurry and make it much drier and easier to process in the rotary kiln. And secondly, the slurry out of the needle has a much higher concentration of sulfuric acid, so it can promote the reaction further with the recycled solid that otherwise will have minimum acid left. And thirdly, this recycled solid from the end of the kiln being at much higher temperature, so you can quickly heat up the slurry, a fresh material upon mixing to facilitate faster reactions and also increase the overall process energy efficiency. Additionally, this rotary kiln, the front end will also equip with baffles and cage structures, aiming for further particle breaking down. So here you can see that actually we are designing our reactor configuration mainly based on our own research findings, but also leveraging the available industrial experience as much as possible. Following our process development strategy and plan, we logically began the scale-up work with the first stage reactor, a double-shafted needle. This equipment is designed to handle the early stage mixing and reaction work. So as announced before, we designed and ordered a pilot-scale double-shafted needle as the primary equipment for our pilot batch reactor system to evaluate its performance in bus applications. So as you see in this main photo, this system consists of mainly 4 sections. Inside the film cabinet on the left-hand side, there's our acid mixing and feeding system, where we prepare our 100% sulfuric acid from oleum. This has to be done safely in a well-ventilated film cabinet due to the high vapor pressure of sulfur trioxide, which is highly toxic and corrosive. So each time we can prepare about 16 to 17 kilos of acid in this tank. The blue equipment in the middle, that's our double shafted needle, where you can see the configuration of the shaft in this photo as well. This needle has a 10-liter operation volume and the design temperature up to 500 degrees. On the right-hand side, that's our HF scrubbing system, which consists of one packed bed column that's operating with concentrated potassium hydroxide solution, 2 heat exchangers, and 2 pumps. This system uses Venturi effect to create vacuum and withdraw the HF gas produced from the needle. The whole system also requires cooling water and compressed air supply, which will be provided from the oleum rig facility in the same factory. In a typical operation of the needle, a minimum 40 to 60% filling of the volume is required. So this is equivalent to about using 4 kilos of crushed bass with 6 kilos of sulfuric acid to produce up to 2.3 kilos of HF and roughly 8 kilos of solid product. This operation is about 50 times larger than our rotary kiln operation. So to matching this process capacity, we also order a ball mill and an ultrasound-assisted screener for better control of the bass particle size which we know is crucial for achieving high fluorine conversion. This pilot batch reactor system was constructed and commissioned last October and has been used for 6 runs so far. By applying the knowledge we gained from laboratory research work, we have achieved most of the objectives with this batch reactor system. We are satisfied with the performance of this needle in the early stage of Bass reaction. Upon inspection of the tested material, we believe this double shaft needle with the current design, it can provide adequate mixing and reasonable grinding capabilities down to a size level of 3 to 5 millimeter. As shown in these comparisons on the left, we can achieve about 80% fluorine conversion using the needle with a single pass, which is almost 10% higher than the laboratory kiln result. And more excitingly, we have recently pushed the fluorine conversion above 90%, reaching a maximum level of 92 to 93%. This is achieved by combining the needle operation with subsequent muffle furnace process with multiple paths, try to simulating the rotary kiln effect. The numbers in red color, this represents the fluorine content left in solid product. So a 93% conversion typically equal to around 2% fluorine content in solid residue. I think as I explained before that we don't expect to achieve 90% or above fluorine conversion directly from the needle output due to its limitations to produce fine enough particle size. However, it was to note that our achievement is actually quite comparable with the standards of current fluorspar industry. Fluorine content in the solid product from current fluorspar process typically falls within a range of 0.6 to 3%. A precise benchmark of less than 1% can be achieved, which is corresponding to about less than 2% calcium fluoride left, or above 96% of conversion. However, we need to note that this precise benchmark number can be only obtained by applying various cutting-edge techniques, including the use of, as Chris mentioned, the pre-kneading reactor and a rotary kiln with proper configuration design and internal slug return system. So pushing every single percentage of fluorine conversion above 90% is actually quite challenging and require considerable efforts. This difficulty arises from the nature of solid reaction and a very low concentration of reactant at the end of the process. Both of them suppress the mass transfer. So our achievement of above 90% fluorine conversion actually represents a significant accomplishment of our research work, given that the fact that the Bass reactions are inherently more difficult than fluorspar reactions. So we also expect that we can achieve slightly better results with the continuous pilot plant operation due to the involvement of rotary kiln with a larger diameter and proper configuration design as a second stage reactor. On the other hand, this relatively large throughput from pilot batch reactor system means that we can produce sufficient solid material with high fluorine conversion and consistent quality. So this will enable us to commence the studies on the separation and the purification of metal sulfate byproduct. So ultimately, I think the target fluorine conversion for our commercial Bass process will balance the process economy and the market acceptable fluorine levels in the solid byproduct. although there is still some work to be done with the pilot batch reactor system, our research focus is now shifting to the next step, which involves the test of the second stage reactor. To do this, our plan is to design and construct a continuous pilot plant to evaluate the performance of two-stage reactor in batch reactions. Besides this main objective, there are still some other tasks that we expect this continuous pilot plant can undertake. For example, validation of the HF produced from batch reaction for subsequent aluminum fluoride production, and also for finalizing the process conditions for operation and determine the scale-up parameters. By considering all of these purposes, we finalized the basic design of the continuous pilot plant, as shown in this drawing. It mainly consists of 4 modules. The oleum production module is in purple color. This is an existing technology, and the reason we plan this is, again, due to the difficulties of sourcing oleum supply in Australia. The batch reaction modules in green color, which involve two-stage reactors, double shaft needle and rotary kiln, as well as a HF washing column. So here we use sulfuric acid to wash the crude HF produced from reactor to remove solid carryover and high boiling point impurities. And this washed sulfuric acid will be then fed into the needle for reactions. As Chris explained, the commercial HF production process will have the subsequent purification operation. But we decided not to include it in our pilot plant because we only need to understand the quality of the HF we produce and ensure it can be purified to the level for aluminum fluoride production with the available techniques. So production of aluminum fluoride is not planned for this scale. This continuous pilot plant is designed with a nominal capacity of 20 kilo per hour bars, which is close to the minimum size that allow for a minimum required reactor diameter for engineering evaluation. A smaller pilot plant would result in a reactor with smaller diameter, which will compromise the adequate mixing and grinding required. And also the mass and heat transfer will behave differently from a commercial scale. So this number also aligns with our rigorous scale-up plan from the pilot batch scale to demonstration and to the full commercial scale, with a controlled scale-up factor of less than 20 between each adjacent stage. So now we have finalized the basic engineering design of the pilot plant, completed the technical due diligence with the main equipment suppliers, selected the preferred international suppliers, and now we are finalizing the technical requirements and the contract details for exchange with these suppliers. So to summarize, moving forward, our technical plan in the near future will focus on 2 aspects. One is moving to the detailed mechanical engineering design and the implementation phase of the continuous pilot plant to further advance our process. And the other is to developing sellable metal sulfate byproduct, given our increasing capability of producing large quantity of solid material with high fluorine conversion. In closing, I would like to comment on that our research work so far has been substantial, especially with the limited results we have. We believe that we made the right decisions, and the steps we are taking can further expand our capability for the process development. So recall the project management plan and strategy we always insist, which is to always consider alternative choice and make best decisions in order to minimize the cost, time, and the risk of the overall project. we'll keep following this philosophy in our future work. Okay, at the end, thank you for your attention.
As the idea comes up, I think you're welcome to raise a hand, ask a question. Fluorochemical opportunities for Australia. It's a topic that me and Mark touched on in the beginning. I think Mark was actually raising the point about establishing a fluorochemical industry in Australia. We've been trying to do that on top of a huge fluorspar reserve now for 40 years. Still no fluorochemical industry. Parts off, comes and it goes. So it's not a straightforward, I've got a resource, now I can do the value chain type thing. But the position on your side is unique, like I've said in the previous discussion. So for me, it's a teaser at the moment. Let's tease out a few ideas, see how you can benefit from looking at this thing value chain wide, and we take it from there. I just want to see if I can. Why is this thing not responding here now? Just go there. Okay, so the purpose of this presentation is to stimulate discussion, some brainstorming, some vision, some strategy formulation on your side specifically then. And then in the broader sense of the Australia establishing a full value chain for chemical production in Australia. See how one can go that. So the content is the motive. Why would one like to do something like this? Apart from the grand intent, resource, what resources are available actually, because that will be driving the motive, possible ways to do that, pathways. I've already touched on it in the previous discussion, and then some conclusion. Do you want to spend time on that? Now, the Alcore project, I've put down a few statements here. You can add if you would like. The Alcore project opens a single entry point into the fluorochemical value chain, and the most important entry point, which is hydrofluoric acid. The reason I put it there is that what I mentioned about the unit cost of production allows you to enter the smaller segments of the value chain, a lower volume but much higher value product. So the margins are better. Like I mentioned also previously, in the HF production as a primary, it's a showstopper most of the time because of the volumes you need, and then finding the offtakes. You know, when you go there past bankable feasibility, offtake is one of the key tick boxes. I'm going to produce 60,000 tons of HF. Who's going to buy it? And that is then, and then you find out that you can split a little bit into here, a little bit into there, and you need to end up with a customer list like this with 50 offtakes. So that is a showstopper. The benefit of the local industry value chain of a country's mineral wealth is undisputed. That is what for us, we are, as Beef Fluor, we are passionately driven by processing Africa's minerals, full value chain in Africa. Because exporting the raw material is you're exporting the wealth of the continent and you leave the poverty behind. So the only solution, in our opinion, for Africa's poverty issues is processing the value chain, building the factories, involving the local community, skill them up, and in that sense you get the mineral wealth spinning in the economy and the dynamo coming from that creates. So same applies here. If you process, now you're in the fortunate position of having a more full value chain approach in your industries. You're not exporting so much of your raw. I've coined a saying a while ago in a presentation in Shanghai. why are you exporting useless rock halfway around the planet? They mine the stuff, there's 5%, 10%, 20% valuable in the rock, and they ship the whole rock. From Africa. So local industry now, I've had a quick look at your fluorspar reserves, and I understand the major reserve, Ian, if I listen to you, is Tasmania side. There's a fluorspar, so putting a kiln there may be a good idea, but now if the Alcore HF production process is there from the bath, it's actually then a good resource. Fluorine is a key component in a host of value chains, from metals to medicines, from engineering polymers to refrigerants. There's a whole host. Isotopes, the medical isotopes, molybdenum, we've come across just recently. In your life, there's so much fluorine without you knowing it most of the time. So in the specialty environment, there's quite a bit of fluorine to go for. So that, the silent Trojan horse, it's a topic that we've discussed in almost every year in the fluorspar conferences. The topic gets discussed about, although fluorine is now slowly but surely getting labeled as a critical mineral, it's still very much, if you go look at the battery reporting and the battery media publications, you rarely find anything about, or ever, about fluorine. But most of the lithium batteries are full of fluorine. The solid-state batteries coming has got fluorine inside. The aluminium that is used as the casing can only be there because of fluorine. So in this silent Trojan horse, take fluorine away, and most of what you experience in your daily life is going to disappear. So for Alcore to start becoming more aware of where this fluorine is functioning in the processes, will point you then towards where can you go with your fluorine value that you get from the waste material. So there's quite a bit of motive to consider the full value chain application of your fluorine that you're going to get out. The easy one is the aluminum trifluoride. And the second easier one, if we go to resource then, is you are developing key resources that are able to drive and feed the development of the LoRa. That is done in specific reference to you as well. The HF from the Alcore project then sets a stake in the ground and provides a launching platform for you to do that. And then the other potential feedstocks, like I've heard Ian saying now about the fluorspar in Tasmania, FSA from the phosphates industry, those technologies are all mature to recover the fluorine. We've got a flow sheet where you can take the fluorosilicic acid and through a plasma process, of which we've got the technology. We've got some of our members in our network has got patents on recovering the silicon as a pure silicon into the solar panels, and then the fluorine coming out goes into the monomers for the refrigerants. From there you can make the new generation HFO refrigerants that hasn't got the high global warming potential, and together with fluorine production, the hydrogen coming out of the fluorine production, out of the electric cell, combining that into the new generation refrigerants. So there are flow sheets that you can draw up, and in most of these value chains, we've got flow sheets. Some of them new type or new flow sheets. So there's I call it our black box. We've got a black box of reconfiguring value chains with fluorine as the component. Tantalum, niobium, we've done quite a bit of work in Uganda, separating tantalum, niobium. Unfortunately, the greed of the politicians took us when we brought the project money. The politicians said, okay, here's my mining certificate, I'll take the cash. Then we say, no, the cash is for the project. You get another piece of paper called a share certificate in exchange for your mining right. So that was the end of that project. But there's on the feedstock side, the recycle. I mean, the batteries. There's a big topic on battery recycling at the moment, with a focus, of course, on the lithium and the metals content of the batteries. But somebody needs to look at. I'll be having a meeting in Perth, Curtin University. One of my old colleagues from Pelindaba, from the nuclear, is professor there. Mark knows him. I don't know if anybody else. Jock Extian, and we've had this discussion just now on the recycling of the battery. The lithium batteries have got fluorine inside, so there's a source of fluorine that can go into. So there's quite a range of sources, of which yours then is the most advanced at the moment. And that puts you in a primary position to consider wider fluorochemical value chain applications. Possible pathways directly into the aluminium industry, I've mentioned it this morning. The alloys, the base metals going into the alloys, titanium, boron. We've designed and we've built those plants so we can offer them to you. To take your HF into the master alloys, and that it offers the opportunity. Actually, we've done quite a bit of test work at the one university on making formulations. Currently, the alloy process is a two-step process. The industry manufactures master alloys, which then gets put into the third induction oven to produce the standard alloy. You can actually combine those two ovens if you've got a nice fluorinated mix of the formula for and we've done quite a bit of work at our university at lab scale. So we've got that results. We've looked at bringing in something like tantalum, for instance. Tantalum gives quite a few physical property positive changes to the alloy. So there's quite a bit of opportunity just in the aluminium industry. So if you're already gearing for ALF3, aluminium trifluoride, going downstream into the alloys with your HF is a very attractive option. It's not complicated processes. It's import replacement of the metal fluorides, that's what I've just mentioned. We've done interesting work. Partially converting about 10% of the AHF to fluorine gas. That's the other part. Our FGen that I've showed you use anhydrous HF as feedstock into fluorine. About 10% of the fluorochemical value chain is straight from fluorine as the building block. So it splits off from the HF into the fluorine. And then those are small volume, high value products like the xenon fluorides, as an example. Very high value, very high profit margins. So the list is actually much longer. I haven't even got the organics in here, either on the medicine, pesticide, herbicide side, or on the refrigerant side, polymers, the other one. We've got some of the French laboratories that we've integrated with over the past year, 4 of them. Montpellier is very heavily involved in grafting polymers, fluorine polymers, different shapes and sizes for different physical property applications. So producing the monomers, we've got plasma technologies that we can produce the mix of monomer that we can then polymerize into either co or terpolymer. So it's the opportunities are endless, in inverted commas. It's the implementation. Okay, so the conclusion of this short is the Australian chemical and associated industries provide a rich and fertile bed, actually. I mean, with all the metals that you are processing already. We're also now not along the fluorine chain, but going into the vanadium, the batteries, which moves us into that space, but not on the fluorine side. But so the development of your vanadium value chain, I mean, Australian vanadium there in Perth has got a saying from pit to battery. So full value chain concept is at play in Australia. So the Alcore project can be a strong catalyst then, triggering on your side exactly that. So the opportunities are plenty. Finding the route is the challenge. There are too many opportunities and too little fluorine. So you can consider a larger plant if you can get enough bath. Okay, any discussion points out of that? First thoughts, you're welcome.
So I had this slide up before, so now really I'm just going to spend a few minutes tying Alcore together. Before then I speak about our second project, our rare earth project. And so really, from what Xiao and I have said earlier today and what Chris has said today, our strategy, Alcore's strategy is to say, right, we have a technology for producing HF from an aluminium smelter bath, so that can produce HF at lower cost in an environmentally friendly way. What should we do with that HF? I think quite clearly in Australia, what you would do is you convert that to aluminium fluoride. There's a significant market for aluminium fluoride here. Australia is number 7 in aluminium production, and our HF market is very small. So the first application, the first business is a plant here making hydrogen fluoride and aluminium fluoride for the Australian market. From then, you've got all the different options you've heard about. That could be export aluminium fluoride. It could be sell hydrogen fluoride directly into the Australian market, although small right now, but it could grow if we can, if we're producing it locally at lower cost. And, ultimately, you could convert that hydrogen fluoride into other fluorochemicals in Australia like Chris has suggested. So I quite like the combination. We have a very clear path to market, produce aluminium fluoride in Australia. Doesn't need to be that big. We're not relying on trying to establish a massive plant. So you can be profitable, a very clear pathway, yet there are all the other options to create more value from the technology, both in Australia and overseas over coming years. So to me, that's the combination you want. You want a very clear path to commercialisation and profit and cash flow, coupled with a variety of other applications that you could extract more value over time. So just to be clear, that's our strategy. Of course, we're always thinking, we're always talking to different parts in the market. Things can change. You never know. Someone comes along and says, some new massive graphite mines are opening in Australia. They need heaps of HF to purify the graphite. How about you just sell HF and don't worry about aluminium fluoride? Yeah, that could happen. But at the moment, let's make aluminium fluoride and sell it to the Australian market. And I'd say the second logical step would be to then do the same thing overseas for the aluminium industry overseas. So we know there are major aluminium producing regions that are producing a lot of excess bath. They also need aluminium fluoride because they're aluminium smelters. So logically, put other Alcore plants, say in the Middle East, in Quebec, in Norway, to service the aluminium industry. Again, that is the plan. That can change if commercial situation demands it. But there's a very clear plan for the next several years. Okay. So that concludes everything we were going to say on Alcore today. So I'll pause again to say, is there any questions about Alcore? Again, you can when we finish at the end of the day, you can ask again. But is there any of that questions on Alcore you've been meaning to ask all day, and now you've just remembered? You would have all probably heard of rare earths. There's actually 15 or 16 separate rare earth elements all across the bottom of the periodic table. They've got lots of different applications, and the different rare earths are used in different applications, often at very small amounts, but they give very particular exotic properties when alloyed with other elements. Demand's growing rapidly, and China dominates the market. That's both on the mining side, where they still mine more than half the world's rare earths, but even more so on the downstream, the processing side. So rare earths have to be separated, then turned into metal, and then turned into products. And China's dominance, in the various segments and sectors, can be up 90%, 95%, 99%. Particularly in the case of the heavy rare earths, which is one set of rare earths, they've got very, very high dominance. Now, the prices of rare earths varies enormously. That chart on the right shows that. They're basically varying by 3 orders of magnitude. So lanthanum and cerium on the left, about the price, the same as aluminium metal, compared to, say, terbium, which is 1,000 times more valuable. And the reason that is because, as I said, there's 15 or 16 rare earths. When you find them in the ground, you find them all. They're always all together. Their relative proportions can vary, but they'll be in a certain proportion. Because we have all these different applications for them, and those different applications are different rare earths and different amounts, you can imagine the relative demand for the different rare earths never coincides conveniently with the proportion in the ground. So by definition, when you mine enough rare earths to get the valuable one to satisfy a particular market, you end up with a surplus of the others that you don't really need. And so the prices of those are really low, and the prices of the one we've got a shortage of are really high. And you can't easily substitute one for the other. So again, you can't just say, terbium is really expensive, so let's substitute lanthanum instead. It gives completely different properties, so there's no point. And then even more particularly, when we say, the rare earth demand is going up a lot and we're trying to find more rare earths, what we're talking about really is 4 particular rare earths. I'll say them once, afterwards I'll use the acronym, but neodymium, praseodymium, terbium and dysprosium, and we call them ND, PR, DB and TY. The reason they're the 4 in demand is because they're the 4 you need for permanent magnets. Permanent magnets are really powerful magnets. If you have a rare earth magnet, the size of a coin, like a 20-cent coin, but a bit thicker, if I hold it near some steel, it'll really powerfully grab on. And so they're used in things like electric motors to provide very high torque, a lot of power. And those magnets represent 90% of the value of the rare earth market, and it's also the fastest growing bit. So really you might say, rare earths, all these different things, the market's growing, it's because of the permanent magnets, that's it. And it's growing fast because of the renewable economy. You need them for these electric motors, such as wind turbines, electric vehicles. Now, there's very simplistically speaking, there's 2 different types of rare earth deposits in the ground. The most common one we call a mineral deposit or a hard rock deposit. So that's the distribution on the left. So Lynas operates sort of one of the top 2 rare earth mines in the world in Western Australia. It's a hard rock deposit. And that distribution shows that the lime green is the ND and PR. So that's about 25% of the volume of the rare earths in that deposit, but it's all of the value. As I said, they're the ones that are worth something. And I mean, you can't even see it on the pie graph there, but the dark green is the terbium and dysprosium. It's almost zero, so there's virtually no value there. Most of the deposit, 75% of it, is other light rare earths, which effectively have almost no value. So that's fine. I said the world needs more NdPr for the magnets. If we just need that, let's just find more, expand Linus's mine, find more like that, let's mine more of those. But that doesn't solve the DyTb problem, the heavy rare earths we need for the magnets. So on the right shows the distribution for a different type of deposit, and it's called ionic adsorption clay. And the key difference there is now that teal green of Dy and Tb is 4% of the rare earths, not zero or close to zero as on the left. And because those rare earths are worth a lot more, in that deposit on the right, the lime green, NdPr, is worth about half the value, and then the small 4% segment of the dark green, the teal, the DyTb, that's the other 50%. And that breakdown is actually the breakdown for ABX's resource in Tasmania. And in fact, for us, our one, that percentage of DyTb is the highest we know of any clay-hosted resource in Australia. And in fact, it's the highest basically in the world that we know of. We're not certain about that, but it looks pretty high. So that makes our deposit sort of more valuable per kilo. And the world needs more DyTb. This is probably where it's going to come from, is these type of deposits. Okay, so very much like I said about Alcore, it's one thing to have a good technology. It's a completely different thing to get a project up. You really need to understand the market and the commercialisation. It's the same. It sounds a bit obvious. It's the same with a resource. It's one thing to have a mineral resource. It's another thing to actually turn it into a mine. This slide summarises all the factors that need to be considered and solved to get a project up. And I'm going to talk about them in turn and explain why ABX's resource is such a good prospect. So firstly, the resource itself, that is where you start from. So ABX is the first company to discover rare earths in Tasmania. And so that map is centred around Launceston in northern Tasmania. ABX has been exploring in that region for 15 years for bauxite. So we had actually a lot more tenements than shown there originally for bauxite. We've mined some bauxite just south of that map, and we're actually going to be mining bauxite almost certainly later this year on the left-hand side of that map. And that's where our main exploration drilling has been for rare earths. So that left-hand section is where our resource is based now. As you can see, we've got several other tenements that are looking prospective for rare earths. And the two key points that differentiate ABX's resource from others, and I'll be saying this a few times, one of them, I've already mentioned, the highest proportion of DyTb of any clay-hosted resource in Australia. And the second is, I'm sorry, it's a bit technical, we say it's got the highest ionic component of any clay-hosted resource in Australia. Basically, that means good mineralogy, which means you can extract the rare earths at low cost. So it's a really important feature of these clay resources. For the geologically minded that follow resource estimates, so this was our most recent estimate just out a few weeks ago, now at 89 million tonnes. That's a more than tenfold increase from our original estimate. We started with 4 million tonnes late 2022. At the time, we were thinking, well, we reckon we could get, if we can get to 50 million tonnes, that'd be pretty good. So we're now at 89, which is great. And that's still only based off 29% of the known mineralised outlines. There's plenty of prospect to grow that resource size. Really, our focus is as much, if not more, on finding the highest grade, best mineralogy areas as opposed to just more tonnes. But I mean, we're still doing both. And it's attracted other companies to the region. There's other people now looking at, they've seen our success and they're going, oh, maybe we should be looking for rare earths in the region. Because we know the area in terms of being active for bauxite exploration for 15 years, we've already got most of the best, most prospective areas to mine. It's not just the resource, but it's what's the current land use, etc. This is the second key point, this ionic proportion. And the reason that's so important is because of its impact on cost. So what it turns out, we being, I'd say, the whole Western rare earth industry, hadn't fully appreciated this. There's a reasonable number of clays around with a reasonable amount of rare earths in them. Most of them, the mineralogy is really poor, basically cost prohibitive to extract them. There's only a small proportion that are what we call ionic, or have a high proportion of the resource being ionic. And the reason that matters, and this is what the graph tries to show, is that if it's not ionic, then you basically need more acid to extract the rare earths, and by doing that you also introduce more impurities into the rare earth product, which then costs you a lot of money to extract. And basically, as far as we can work out, as soon as your ionic proportion drops a bit, you're going backwards. So the cost of extracting becomes more than the value of the product itself. So that's what that graph shows. On the right, your blue line, your operating cost, is now more than the red line, which is the product. So there's no point, you've got no hope of mining in that product because the revenue is less than your cost. And so ABX is towards the left-hand side where the operating cost is low, and there are very few prospects like that. In fact, we think we're the only one in Australia at that part of the curve. And there's not that many around the world either. Okay, so we think we've got good resource, we think we've got good mineralogy. Still, you need some other things to get a project up. The next one is infrastructure. You need to be able to get the product to port. You need power, you need water, you need people, you need engineering. And again, northern Tasmania is a fantastic place for that. So we're less than 20 kilometres to the main highway. We're less than 100 kilometres to the Bell Bay port on the northern side of Tasmania, where we've previously exported bauxite, and we will do again. We're only 50 kilometres from Launceston, so that's access to labour and skilled engineering. I live in Melbourne. I can be on our drill site like within 3 hours of leaving home. Basically, I can get to the airport, less than an hour flight, 45-minute drive, and I'm at our exploration site. Very convenient. And water, no problem in Tasmania. Energy, we're close to transmission lines, and also obviously Tasmania has a high proportion of renewable power. And then another dimension is jurisdiction, especially important in rare earths, given its geopolitical issues and its importance to military technologies. So Australia, extremely favourable. We're talking to potential, off-take customers around the world, and they all love the idea of being able to get a rare earth product from Australia. There's, sort of none better. Tasmania itself has a long, proud history of mining, especially northern Tasmania. It's a supportive environment. The Tasmanian government is keen for more mining. And then in the Westbury region in particular, where we're operating and where our resource is and where we're drilling, is mostly commercial forestry. So the land's already affected. It's a fairly straightforward commercial negotiation to get access to the land for mining, and the landowners are generally supportive. Some areas, in northern Tasmania that might be less receptive to mining we know where they are, and we don't try and explore or mine there. We're very familiar with the area. And then you always need great people. I made the point before on Alcore, with a small team, you need great people. It's the same on the rare earths. So we have, I think, it's certainly valuable, and I think it's fairly distinctive combination of geology and chemical engineering. Rare earths, I mean, the exploration and the mining, that's what it is. You need geology and mining, but the processing is real hardcore chemical engineering. You need knowledgeable chemical engineers. There's not that much knowledge in the West about it, so we need highly capable people to develop and scale up that process. That's what ABX has. We've got Ian Levy, who, leading geologist, who, without him we would have never even realised, I don't think, we had the rare earths. But we've also got good engineers that can go, okay, how are we going to process this ore into a product that customers want? And as part of that, our people, I mentioned before, but we have deep experience in Tasmania. So for example, our operations manager, who manages our exploration drilling, he's been leading that sort of work for over a decade in Tasmania, whether that's bauxite mining or bauxite or rare earth drilling. So we've got people with the technical capability and the experience in the area. So what we say, it's true, is that we think we tick all the boxes for an ionic clay rare earth project. So there's two things there. One, we tick all the boxes. We've got the resource, the mineralogy, the jurisdiction, the infrastructure, the people. You need all of those things. If you're missing any of those, it can make it challenging. But then we've got our two distinctive features that separate us from others. First one, again, the highest proportion of DYTB of any clay-hosted project in Australia. That makes our product more valuable. And the second is the highest ionic proportion, which means basically we have the best mineralogy and therefore contributes to lower cost production. So it's those two things that are our distinctive feature. And I can tell you, in my talk to lots of companies in the rare earth value chain, the big companies in Australia and overseas, they understand. They go, yes, Mark, we understand, we agree with ABX's own self-assessment of their prospectiveness. We think you've got a good prospect here. So what we're trying to do, and we hope we can pull it off, is bring at least one of those parties into our project to partner with us to really try and accelerate this project. The world needs more rare earths like now. And another advantage of the clay projects is they can be started at a smaller size. So let's get cracking. We've got a good resource already. Let's do the metallurgy work, the economic studies, and try and get into production. And just to summarise that, our plan, we want to produce a mixed rare earth carbonate. So that basically means you dig up the ore, you separate out everything that's not rare earths. You're left with a single product that's all the rare earths mixed together, still in a carbonate form, so it's not pure metal. And you sell that to an existing refinery who separate it into the individual rare earth oxides and then turn it into metal. So we're talking to all the refineries that exist and are planned around the world. And so over the coming 6 to 12 months, sort of focusing on the metallurgy work and the economic studies, continuing that customer engagement and trying to get a partner. We still will be exploring, say, with a focus on finding the highest grade zones, which would be the ideal place to start a project. And so just to summarise once more, and to reflecting on my own experience, I've been involved in a lot of new process development over 20 years. Some ideas you start off thinking, oh, that looks really cool, really compelling, and then you do a year's work and you go, actually, I'm not sure, there's a bit of a problem, we can't solve that technical problem, or the market's not as big as we thought, or the customers don't seem to like what's going to be different about our product. on both Alcore and on rare earths. We think these are very compelling opportunities. All our discussions with potential customers support that. Therefore, we pursue both projects, and we're trying to create projects. We're not just trying to mosey along for a while thinking we've got something okay. We actually want to see Bath recycled in Australia, producing aluminium fluoride, selling it to smelters, and on the rare earths, we want to be mining rare earths, making a mixed product and selling that to a refinery who takes it through the value chain.
So, thank you, Mark. So it's left for me now to thank Chris, Chow and Mark on all our behalfs for excellent presentations today. I trust everybody who's taken the time to come up here for the events today has learnt a lot, as I have, on two exciting projects that ABX has on its agenda. The big takeaway I would like you to go away with today is that ABX Alcore is rich in assets. That is our big strength. We've got two very, very good projects in front of us. We have proprietary technology in Alcore, and we have crossed the Rubicon with our announcement today because we've gone over 90% recovery. And that's what we've been seeking to achieve as a benchmark to demonstrate to ourselves, first of all, but to the wider investment community that we have a commercial project. The interesting thing in that regard that I've learnt today for the first time from Chris is that there's a strong possibility that we can reprocess the aluminium sulphate back into our Alcore plant, and that is significant if that can be proven, because as we make the aluminium fluoride, we produce two sulphates, the main one being aluminium sulphate, and as a board with Mark, we've been debating what to do with that and how to commercialise it. But today we learnt that it could actually become part of the production, and if that's true and we can recycle that back through the plant, that is very, very significant. So we'll go away and mull over that and get Mark to work on it and see where that takes us. But that, even if there was nothing else, has been a very significant learning from today. So what are the next steps? The next step for Alcore is to get working on the first continuous plant. We do anticipate at this stage that will be in Tasmania. ABX is a listed company, so there are things that we have to hold back on until we've completed discussion, but I wanted you to know today that as a board, with Mark's assistance, we are quite advanced in discussion in that regard about accessing a site for our first continuous plant, together with sufficient financial resources to get that underway. And I'm quite hopeful that those discussions will be fruitful in the near future, but they're ongoing as we stand here today. The next step in the rare earths, as Mark said, is some more drilling and the production of the first carbonates. The drill is working today, in answer to your question, so we're actually drilling today down there. But when you saw the map go up on the wall, you can see the dark purple, if you can remember what was on that map. The dark purple represents where, as Ian calls it, the honeypots are. And one of those, well, they are our candidates for the first extraction and then production of carbonate. The message I want to leave you about the rare earths today is that as a non-scientist, a geologist, it's a bloody good resource, right? That's what it is. There's nothing else to say about it other than that, frankly. And our phone is ringing and people are wanting to talk to us about it. So, you know, options are opening up for us now that we've got close to the 100 million tonne mark. You know, Ian used to tell us initially that we might get to 50. Well, you know, we've got to 100 virtually, with 29% of our area drilled out, and we've got those two big areas to the south east of Launceston yet that we haven't even started on. And one thing we know about Ian is he knows what he's talking about when it comes to geology, so we should take notice. So I'm very, very strongly of the belief, as I stand here today with you, that what we have is very significant. Proprietary technology with Alcore and a true ionic adsorption clay hosted rare earth element province in Tasmania, rich in dysprosium and terbium. And that the profile of our resource in Tasmania matches that of the ionic adsorption clay deposits that are being mined in China and Myanmar. And that is very, very significant because there are very, very few of those around the world. So it shouldn't come as any surprise to you that our phone is ringing, so people are approaching us about it now to have serious discussion with us, including government, and we are engaging in those discussions. So what do we need to be able to develop these to their maximum potential? Partners, in a word. Are we working on that? Yes. Please go away from today knowing that, as Mark sort of alluded to right at the end, that our focus is very much now on getting those financial partners on board with us so that we can develop these two very good opportunities into strong commercial businesses and deliver results back to shareholders. And finally, I thank everybody for their patience. Please understand that your frustration is shared by your board. All of the members on the board have big shareholdings in ABX. We're staying the course. We urge you to do the same. And I have strong faith that this coming financial year will be productive for our shareholders and for our business. So thank you for coming today to get an update, and I wish you a safe journey home.